Welcome back to the workshop. We want to continue taking a look at functions. And in this case, we're going to return back to an idea about functions that we're already familiar with or should be. And that is function composition. So let's take a look at that. We begin by first reflecting back on the idea of being one-to-one and onto, and then move on to the idea of composition. So a function that is both one-to-one and onto is called a one-to-one correspondence. And you might ask yourself, well, that's a bit of a mouthful. Isn't there a shorter way that we could say that? Yes, but unfortunately, we're not using that language in this course. If you would like to, I'm okay with it. You can call it a bijection. A function that is one-to-one is also called an injection, and a function that is onto is also called a surjection. So if it's both an injection and a surjection, then it is called a bijection. So that collection of language is typically used in other math classes. Here in a discrete math class, right, one-to-one and onto are maybe a little bit more used. Maybe not. Maybe it's just this particular textbook. But anyway, bijection is a shorter way to say that. So note that for us to observe or see that a function is a bijection, what we would have is that for each element in the codomain, there is exactly one element in the domain such that f of x is equal to y. Okay, so it's onto, so for each element we can find such in x. But since it's one-to-one, it would be exactly one such x. All right. So our next definition is just of a particular function, and we won't be maybe referring to it quite so explicitly in our discussion, but it is discussed in a textbook, and it should lead to some observations that you make either through our discussion here that aren't explicit or in your homework that you look at as well. So for any set A, the function given by I sub A from A to A, right? So it's just some function I from A to A defined by I sub A of x is equal to x. So whatever you put in is exactly what you get out. It is a one-to-one correspondence. If I want to get y out of it, I just plug y into it. And there's only one way to get y out, and that's by plugging y in. So it is a one-to-one correspondence. And right, it's the identity function. Identity means that it's not changing what's going on. The idea of an identity is very generic. We have an identity for addition, right? 0. You add 0 to anything, and it doesn't change the number you added it to. Multiplication, 1. You multiply any number by 1, and it doesn't change the number you multiplied by 1. Okay, 3 times 1 is still 3. Identity function, whatever you plug into the identity function is what you get out. It didn't change that thing. But furthermore, this is also the identity function for what we'll find to be composition. So suppose we have a function f from a to b and a function g from b to c. Here we want to define composition. The composition of the function f and g is the function. We're going to write it as g composed with f, and it goes from a all the way to c. So when we compose them, we're skipping over the set b. And the composition is defined by g of f of x is, right, so that's how you would say it, g of f of x is g of f of x. Okay. So this is the definition of composition. You might notice your textbook gives the notation slightly differently. We say g composed with f of x, and the textbook says g composed with f of x. And the reason that I'm not using that here is because those of you that are familiar with the algebra of functions might recognize that this is typically the notation for multiplication of functions. If I take two functions and multiply them together, that's the notation that I would use. So it's ambiguous. Using this composition notation makes it unambiguous. This is clearly composition. This, for our textbook, is composition. So if you see GF, it is composition. But if you go to a different textbook, it might not be. So our notes will use this. The textbook will use this. Make sure you understand that they're the same and that this is slightly ambiguous. Okay. All right. So let's take a look at just a nice visual representation, another diagram for us, if you will. So let's say we have our set A and our set B and our set C. So we have the function f that goes from A to B. So let's throw a couple elements in there, really just one. So let's say we have element X, element Y, and element Z. Okay, so we've got X, Y, and Z. We have function f, function g. G would take Y to Z, and f would take X to Y. So we would travel along, and the composition would simply take, right, G composed with F would simply take X and bring it directly over to Z. So that's the idea of function composition. All right, so in this case, or for these couple examples, we just want to determine the formulas for the composition of functions. Again, I'm assuming that this is something that you're familiar with, so I'm not going to spend too much time on it. If you need further examples, there is a large number of examples available online simply by searching examples of composition of functions. Easy enough. All right, so determine the formulas for f composed with g and g composed with f. All right. F composed with G. So you might notice that some of my circles look like dots. We should be careful about that, but it should be a circle if there was any confusion. So F composed with G of X is F of G of X. And so what I'm going to do is I'm going to leave it as G of X, and I'm going to plug it into F. So F in this case is 2 to the X. So this is 2 to the, well, I'm plugging in G of X. Okay, simple enough. Now what is G of X? Well, that's 5x plus 7. So this is 2 to the 5x plus 7. Okay, easy. Well, what about the other way? G composed with f of x is G of f of x. And here I'm just going to plug f, the letter f of x, into the function g. So I have 5 times f of x plus 7. Now from here I say to myself, well, what is f of x? Well, f of x is 2 to the x, so this is 5 times 2 to the x plus 7. Now in this case, I'm writing the dot for multiplication, because if I were to omit that dot and just have 5 times 2 to the x plus 7, you might think that's 52 to the x. So I'm including the dot there to make it as clear as possible. Another way that we could do that is 5 times 2 to the x. Although you could also put the x inside the parentheses. So there's options there, but you don't want to put the 5 next to the 2 without any notation. All right, so that's good. For our next example, let's see here, we have f is 3x plus 2, and g of x is x minus 2 over 3. So composition, f composed with g of x is f of g of x. And so we have 3 times g of x plus 2. And that would be 3 times x minus 2 over 3 plus 2. 3 divided by 3 goes away. X minus 2 plus 2 is just X. Interesting. Interesting. And then G composed with f of X is equal to G of f of X, which would be f of X minus 2 divided by 3. And f of X is 3x plus 2. And then we have a minus 2 divided by 3. Of course, 3x plus 2 minus 2 is 3x. 3x divided by 3 is just x. Interesting. In our second example, for B here, f undoes what G did, 2x. So f undoes whatever G did to x, but it's also the same way the other way around, right? So when I plug x in, I'm going to plug it into G, and it's going to subtract 2 and divide by 3. And then f is going to do the opposite things and give us back x. But the same goes for the composition the other way. Whatever f does, right, it's going to multiply by 3 and add 2. Then g of x is going to undo what f did. So f undoes what G did to x, and G undoes what f did to x. Interesting. And that's a very particular and special situation that we want to talk about, recognize, and know, and we'll do that in our next video. So one more video for this section where we talk about inverses. I'll see you guys back in the workshop in just a moment.